Okay, good morning. All right, let's talk more about series. What else are we going to talk about? Okay, today we're going to look at 11.5. Most students find this section relatively easy compared to the stuff we've been doing. So you'll probably find this a little bit easier to understand. We're going to look at a type of series called alternating series. So what these are are series with terms that have alternating, that means plus and minus signs. So one is plus, the next one's minus, next one's plus, minus, so on and so on and so on. They look something like this in general. Okay? This minus 1 to the n plus 1, this is what's causing the plus and minus signs. Minus 1 is always 1 if the power is odd, but if the power is even, this is positive 1. So notice when n is equal to 1, we have minus 1 squared. That gives me a positive number. And then n is equal to 2 gives me a negative. In this expression here, these bn's are always positive. We'll let the minus 1 to the n plus 1 give us the alternating signs. But these things are always positive by themselves. Okay? The question is, how can we check if an alternating series converges? And if it does, can we find the sum? So let's go back to the harmonic series for a moment. Okay, we know the harmonic series is a divergent series. But what we're going to do today is to change the signs of every other term. So instead of 1 plus 1/2, I'm going to do 1 minus 1/2 plus 1/3 minus 1/4. So we're going to come up with what's called the alternating harmonic series. One minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus dot, dot, dot. All right, so how do we write this? We need an alternating sign, so that's our minus 1 to the n plus 1. When n is 1, we get a 2 here for the power. That gives me positive 1. And then we take the same expression, 1 over n here. Okay, so again, this is always, 1 over n is always positive. We'll let the minus 1 to the n plus 1 give us the alternating signs. Okay, so let's check out whether this alternating series will converge. And let's do that by checking out the partial sums. Remember, S sub n is the nth partial sum. And if the partial sums seem to be settling somewhere, then we can say this is converging. And we can probably also kind of eyeball what the actual sum is. Okay? Okay, so when n is equal to 1, that's just the first partial sum, which is the first term, and that's 1. The second partial sum is the first two, 1 minus 1/2. So that's 0.5, right? Then the third partial sum is 1 minus 1/2 plus 1 over 3, and that gives me 0.8333 repeating. Get the idea. So the next one, I'll just write out a few here. Okay, so it's up to the fifth one. Okay, so for this one here, it is not quite enough to see what's going on. You'll come across series that converge slowly, like this one. It is still wildly changing. Let's do a few more. In fact, I'm going to skip a few numbers, go directly to 10. $20. All right, between 10 and 20, it is still changing quite a bit. Let's go a few more, about 50. Now, obviously, I didn't do this by hand. I had a computer help me. 100. 6, 8, 8, 1, 7, and 200. All right. So between 50, 100, and 200, it appears to be settling down now. It's 0.68, 0.688, 0.69. Okay. So it appears to be settling down. After a while, based on these numbers here, the sequence of partial sums, we can confidently say it is going to be converging to somewhere near 0.69. Now, what this number is, that's a secondary importance. But first question to answer is always, does it converge? And we can kind of see that it appears to converge. Take a look at what happens if I graph these points. All right, so you can see these are the ends and these are the partial sums. We started at 1 way up here, and then 0.5 brought me down to here, and then 0.8, so up here, 0.58, and so on. And eventually, it's settling down. Right? Remember, a way to tell if this thing is converging is there a horizontal asymptote? There appears to be one, right? .69, 0.7 area. So this thing is converging based on what we see here. Okay, so the first thing we see here is that the regular harmonic series is diverging. But if we change the signs alternatingly, then the alternating harmonic series is converging. So that's kind of suggesting that the requirement for a converging alternate series is a little bit less stringent than other series. So let me give you the two requirements for an alternating series to have to converge, and then I'll explain why why that's the case. So here are the two conditions. The first one is that b to the m, b sub n plus 1 is less than or equal to bn for some n. Well, let's put it this way. For some sufficiently large n. So what this in words is saying is that the terms Bn is decreasing eventually. It can be changing unpredictably for a little while, but eventually it should settle down. And we want this to eventually be decreasing. And this is what we see in the alternating harmonic series, right? 1, 1/2, 1 over 3, 1 over 4. So all the terms are decreasing. So we have that in the last example. And then the second requirement is the limit as n goes to infinity of Bn must be going to 0. Okay? So where have we seen this before? The second condition. That's a test for divergence, right? Yeah. This is what we always check the first time. So this is basically the test for divergence, which is something we already check. Right? So really all we need to make sure is that the terms are ultimately decreasing. If it's decreasing for all possible n's, then that's great. But that's the thing we need to see. And as you can see, the alternating harmonic series meets both conditions. All the terms are decreasing, 1, 1/2, 1/3, so on, and eventually going to 0. Yep. Okay, let's find out why it works. And we can also find out the sum by doing this exercise here. So here's a line with numbers, real numbers on it. So remember, here's what we're doing. B1 minus B2 plus B3 plus B4 minus B5, and so on. And let's also assume that all the terms are decreasing and also eventually going to 0. Okay, so the first term is going to take me from, I start with nothing. My first partial sum is B1. So it starts taking me over here. So that's my plus B1 right here. That's my first partial sum. And then I'm subtracting B2. So I'm going back here. Also, B2 is smaller than B1. So let's say my B2 puts me over here. Let's do S1 here. So here's my second partial sum, right? And then I have my B3 going back, but also smaller than B2. So here's my third partial sum. Okay? And then if I keep doing that, here's my negative B4 plus B5. Notice they're getting smaller. Minus B6 and so on. So that's going to put me here, here, here. Right? As long as each step I take in either direction is smaller than the previous one, it will eventually put me somewhere between where I started and the farthest to the right I went. See that? Think about it this way. If I'm standing here and I take 2 steps forward, and I take 1 step back, then half a step forward, a quarter step back, and eventually, where am I? Eventually, I'm at a fixed location, right? Same thing here. As long as my steps are decreasing and I'm changing direction, I will eventually be trapped between somewhere in the middle here. Okay? Does it make sense why this is converging if these two things happen? And also, if they keep getting smaller, then I keep taking smaller and smaller steps. Eventually, I am not going anywhere anymore. So where is the true sum on this picture here? Can you kind of spot where the true ultimate sum would be? Like somewhere here? Do you agree? Yeah. Exactly where, we don't know, but looks like somewhere between there and there. Now let's find out how we can find this true sum. And we'll use the same picture, but not as many numbers on it. And we saw earlier remember, the true sum is somewhere here. So S1 puts me here, S2, S3, S4, and so on. Okay? Just pay attention to the first one and the second one. This is plus B1 minus B2. If you look at this here, notice we can always see that the true sum is somewhere between two consecutive partial sums. Always between 0 and S1, obviously, between S1 and S2, between S3 and S2, S4 and S3, and S5 will be here somewhere. Always between two consecutive sums, right? So let's see. S of n is A1 plus A2 all the way to AN. Oops, no, we're using B here, sorry. B1 minus B2 plus dot, dot, dot. And then the next partial sum is that. Okay? And also notice that each time we add a partial sum, we get closer to the true sum. So in other words, S of n plus 1 is closer to true sum than the previous one, right? It's always between two consecutive sum, but the higher partial sum is always closer to the true sum. In fact, what we're going to see, therefore, is that the difference between, let's take S3 and S4, for example. The difference between S and S3 is smaller than or equal to the difference between S4 and S3. So once again, imagine n is equal to 3. The difference between this and that is smaller than the difference between that and that. See that? Yep. And the difference between these two is that extra term we added on there. And that's going to be b sub n plus 1. We're taking the absolute value, so just taking the positive term here is all we need. And this will allow us to find the sum, or at least narrow down the remainder. So let me write down that again here and then explain that a little bit. So read it from the left to the right. Ignore the middle one here, for example, for the moment. This one is saying that the magnitude of the remainder, or in other words, the difference between the true and partial sums is the magnitude of the first ignored term. That's the next one. I do partial sum up to 5, for example. Then I look at how big B6 is. And how big B6 is the maximum error I made by cutting the sum short. Okay? You go up to 5 partial sums. The next one, B6, it tells you how big, the maximum, the biggest possible error you have made. Let's take the alternating harmonic series back so you can see that. By the way, look at the power of that minus 1. Does it matter if I put plus n plus 1 or n minus 1? Same thing, right? For whatever n I want to put in, 1, for example, this is 2, this is 0. They both start with a positive term. This is just alternatingly changing signs. So really it doesn't matter if you do minus 1 to the n plus 1 or minus 1 to the n minus 1. You get exactly the same series either way. So you might see this written in both ways when you look at the problems in the book or examples. And from earlier, from the table I showed you, we saw that the fourth partial sum is 0.58333. And suppose that's where you stopped, and you want to know how close that is to the true sum. Okay? So let's look at what the series are saying. 1 minus 1 over 2 plus 1 over 3 minus 1 over 4, 1, 2, 3, 4, 5, 6. Oops, I went too far. Okay, everything up to minus 1/4, that's my fourth partial sum. 1, 2, 3, 4. This next term here, this tells me how big the remainder is. So that means my partial sum, fourth partial sum, is off by no more than 0.2. Probably less, but no more. That's the absolute maximum error I could have made. Let's look at the next one, for example. My fifth partial sum, based on my table, is 7.78333. Okay, my error is the 1, 2, 3, 4, 5, the sixth one. So the error, absolute value of the error, is less than 1 over 6. It tells you the magnitude, but it doesn't tell you the direction. So you can kind of see whether it's an over or underestimate by finding a few of these, but this alone doesn't tell you which direction you're wrong. It just says that you're within that window. And of course, you can see the more you go, the better your accuracy is, right? And if you can capture all of these, then eventually it will be perfect. Okay, let's do a few examples. First of all, questions about the convergence conditions and the partial sum, or the accuracy of the partial sum? Good? All right, let's do this example here, again with the alternating harmonic series. How many terms do we need to add so that the partial sum is off by no more than 0.01? And that's a very, very practical question. You can add all of these, and the question is, how many times do I need to do that so that I have this desired accuracy? So here's what we're dealing with, right? All of these things. And remember, the error that you made here is no bigger than the first term that you ignored. So that means what we need to have is we want to have the error equal to the first term that's ignored to be less than or equal to 0.1. The first one that I ignore in general is 1 over n with an alternating sign. So we're just tracking the magnitude. So the minus 1 to the n minus 1 part, that doesn't change the magnitude. It changes the sign. So we ignore that. Right? So let's see. If this is the case, then what do we have? Divided by 0.01. And what do we see? 100? Right? 100. So this is saying that 100 and beyond, all these terms are smaller than or equal to 0.01. That means I need to add everything up to the one before that. So S99 or S100, either way, should be good enough. The 99th one will have an error that's exactly equal to this. The 100 will have an error that's starting to be less than that. So bare minimum is 99. But if I'm going to be safe to be exact, to be below it, then I need to go to 100 or more. Question about this? Okay, so that's one nice property that no other series have. Okay, more examples. First question is, does this thing converge? If so, then let's find out how many we need to add to be within a certain accuracy that we want to have. And this time we'll go with 0.001. So let's check convergence first. What's the first test we always use? Right. And the nice thing about that is that we're going to do this anyway for alternating series, right? So let's get it out of the way. So is that true? Yes? Yeah. Good. So now what else do we need to see happening for alternating series? There are two conditions. Decreasing, that's right. So that's the decreasing part. Okay, so remember these B are just the part without the minus 1 to the n plus or minus 1. Question? Yeah, we can have either one. So you're right. We can have equal to, and equal to if this happens. Since we checked this already happening, I'm just looking for strictly less than to check the decreasing. But you're right. We can have less than or equal to. So together, this ensures that it's always decreasing. So this, again, is the part without the minus 1 to the power, just the expression there. B n plus 1 for this expression, that's a 1. So we need to see this happening. Simplify a little bit. All right, so now we got to check if is 1 over 3n plus 7 less than or equal to 1 over 3n plus 4. What do you think? As long as n is positive, right? This is always true. This is a bigger denominator. So yes. In fact, it's for all the n's. For any positive n, this is always true. Bigger denominator given the same numerator in each expression. This is always true. So what's your conclusion? Converge, diverge? We met that condition, we met this condition. So this converges. Okay? Okay, so this thing is going to converge. Therefore, it's got a sum. And to find sum, we just add a bunch of things together. We want to do that until we're within 0.001. So if I add n terms, then Sn is accurate within Bn plus 1 of the true sum. Right? That's what the remainder estimate tells us. After I got n, the next one that I ignore, the magnitude of that term, is the accuracy term. And Bn plus 1, we did that earlier when we were checking the decreasing thing. This guy right here, this is Bn plus 1. Right? So that's 3n plus 7. And we want this to be within 0.01? 0.001, sorry. Yeah. Okay, so if I add n terms, then the next one, the one I ignore, tells me the accuracy. I want this to be strictly less than or equal to 0.001. The less than, the equal part tells me where to stop. The less than tells me after that, I'll have smaller errors. So this is pretty easy from this point on. Divide by 0.001, and we get, what is this, 1,000? Yep. And here I found out that n must be greater than or equal to 331. In other words, S331 is the first one that's going to be within that accuracy I specified. If I go any more than that, then it'll be closer and closer to the true sum, and it'll have smaller error than that. But I need to go bare minimum up to the 331st partial sum. Question? Yeah. Because I can do either one, right? The previous one, I did this one because it was easier to check. It was a much simpler expression. So this tells me I need to, so the interpretation here is slightly different. This tells me what I need to, where I need to go to stop to get this kind of accuracy. This one is the one before it. If you do n plus 1, this tells you where to stop. If you do just n, then tells me the one before that is where you stop. You're off by just one before or that current one. So yeah, I should have gone the n plus 1 here just to make it clear, but do the n plus 1 way. That way the n tells you where to stop. Okay? Does that answer the question you got? All right. Okay, one more thing about this decreasing thing. Whoa. The decreasing requirement in the convergence test here let's see, let's write this way, can be met as long as the terms eventually decrease monotonically. It doesn't have to always decrease. It's okay for a few terms to change. For example, if I have this series right here, notice that, again, just looking at the magnitude here, ignoring the plus and minus, just comparing the magnitude, everything from this point on the terms are decreasing. But these two are kind of out of the order here, right? We actually went from 1 to 1.5. There's a jump here. This is okay. This is still eventually a converging series because we have this happening. So what's going on here is if you ignore these two, then you got a very typical alternating series that converges. and then you're adding on 2 or however many finite numbers. Those things don't change the convergence. So this is okay. As long as this eventually happens, then we can be assured of convergence. So this is okay. And sometimes it's easier to check the decreasing requirement by taking a derivative. So one last example to show you how that happens. Oops, that's a 3 here. What happens if I left that as a 2 down here? It will be a divergent series because the terms don't go to 0. So, and then that's not interesting. Let's look at this thing. More interesting here. Okay, so first requirement as usual. The -1 part really doesn't matter, so you could leave that out if you want. Right, and this clearly goes to 0. The denominator is going to dominate the numerator because of the higher power. So that's good. We want to see that happening. And now we want to see if this thing is decreasing. And now things get more complicated. It's a little bit harder to check the way we did earlier. So what we're going to do here is to again imagine this came from a function. All these terms came from a function, a continuous function that we sample at a few different ends. So this function gives us the terms that look like that. Now, if the function is decreasing, then these terms are also decreasing. We've seen that before when we did the integral test. So take the derivative. You know how to do that, so I'm going to skip that step and just look at the derivative. And you can see that, as you know, that if the derivative is less than 0, then the function is decreasing. So what we want to see is, therefore, this thing decreasing, less than 0. And once again, this part down here is a square. That's always positive. Right? And x is always positive, too. Because how we get the n's are always positive, 1, 2, 3, 4, 5, and so on. So these x's are also positive. Therefore, we just need to have 10 minus x to the 4th to be less than 0. Or x to the 4th greater than 10. And that gives you x greater than 1.78. And obviously, you can't go past 1.78 terms. So this is saying that after 2 terms, n is equal to 2, all terms are decreasing. Just like the last example I made up here. Exactly the same situation. After 2, n is equal to 1, n is equal to 2. After that, everything is decreasing, so therefore this will converge. So this is a convergent series. Because the terms are eventually, ultimately decreasing, a finite number of terms can be out of order. Okay, that's it for today. See you Wednesday.
love to do